A very good morning to all of you. In this session, we will discuss about unification in resolution. We have already discussed unification in the previous slides, but here we will discuss in detail. Unification is a matching procedure that compares two literal and determines whether there exists a set of substitutions that can make them identical. So, if such a substitutions exist, they are called unifier. Here we can see the example. Here we have likes x comma cookies. Then likes Tommy comma cookies. So here we can compare x and Tommy. So if we substitute x as Tommy, then it will matches with this one likes Tommy comma cookies. So after substitution, likes x comma cookies become likes Tommy comma cookies. So both literal become identical. So unification is successful. So actually why it is needed? In first order logic, literals may contain variables. So the resolution actually requires exact matching of the literals. So unification finds the substitution that make the matching possible. So we will see the unification algorithm. It is actually carried out by a recursive procedure that compare the predicate names and matches the constants and variables and applies the substitution. So this procedure is called the unification algorithm. So unification actually finds the substitutions and this substitution replaces variables with the constants, and if no substitutions can make the literal identical, so that means the unification fails. So unification is actually essential for first order predicates. So here we can see that unification is a recursive matching algorithm that finds a set of substitution that make two literal identical, enabling the resolution in first order logic. The resolution combines two clauses by finding complementary literals using unification to match them. So that means in the case of resolution that eliminates the complementary literals and combining the remaining literals to form the resolvent. For example, it is given student not student of X or intelligent of X. That is one clause. And next clause is student Ravi. So if we are comparing these two, then we cannot remove the complementary letters. But if we are considering X as Ravi, then the first clause will become not student Ravi or intelligent X. Then we can compare these two and we can compare the complementary literal student Ravi and not student Ravi and the resultant after unification, the resultant after substitution, the resultant will be intelligent Ravi. So we are removing student Ravi and not student Ravi. Then the remaining resolvent will be intelligent Ravi. Here exists Ravi, so we can put intelligent Ravi. So Ravi is a student, then Ravi is intelligent. So this new fact is inferred logically from the given clause. So the resolution actually combines clauses by identifying the complementary literals, unifying them, and producing a resolvent by eliminating the complementary pairs. So here we can see the example. Uh, there is two clause not likes x comma sweets and like x comma cookies. So here the second clause is likes Tommy comma sweets. When you are comparing these two clauses, here in the first case we can put x as Tommy, but second case it is not possible because you can see here in likes there are two parameters are there. First one x and sweetie, second one x and cookies, and the second clause we can see Tommy and seeds. If we are comparing with the first clause, first term there is x comma sweets, it is matching. But second is x comma cookies, but cookies and seeds it's not matching. So we can compare with the first one, and here we can instead of x we can put Tommy. So these two we can remove. Not likes x comma sweets and likes Tommy comma sweets we can remove because x is Tommy. So the remaining resolvent will become likes Tommy comma cookies. So here another one you can see here, likes X comma ice cream, likes Tommy comma cookies. So here we cannot compare these two because the second the clause there are two parameters X and ice cream. The second clause we have Tommy and cookies. It is not matching. The constant is one, first one constant is ice cream. Second clause the constant value is cookies. It is not matching. So we cannot unify this. Then the next example you can see parent x comma father of x. Parent Raj comma y. Here x can be Raj and y can be father of Raj. So this is the unification here. X can be Raj and y can be father of Raj. Here we can see the function unify p comma q equal to theta. So here theta is the substitution. That means a set of variable bindings of the form variable slash term. So similar to this, x is the variable and j is the term. So variable slash term. In this form, we are representing the unification. So if such a substitution exists means the unification succeeds, and if no such a substitution exists means unification fails. So here we can see an example. How does John know? So this is represented as knows John comma x knows John comma j. So from this we can identify that here x can be j. So if x is substituted, x can be given as j, then we can say that this j knows John. So here the predicate and the first arguments are matching and the variable x can be replaced by j. And second case you can see unify knows John comma x known y comma b. So if we are comparing these two, knows John comma x and knows y comma b. Here y must match John and x must match Bill. It is possible, right? So we can say that here unification is possible. X can be Bill and y can be John. Then third one, unify knows John comma x and knows y comma mother of y. So here y match with the John. It is fine. Then x match with the mother of y. That means y is John, right? So mother of John. So here y can be John, then x can be mother of John. So here also unification is possible. Here you can see x can be mother of John and y can be John. Then the fourth example. Here you can see that John comma knows John comma x and knows x comma Elizabeth. Here what will happen? Here x can be John and x can be Elizabeth. Is it possible? So it is not possible. That means one variable cannot take it two different constants. So here the unification fails. Next we will see standardizing apart. In the previous slide we have seen that variables can unify with the constants, functions or other variables. A variable cannot be bound to two different terms. So here we will see standardization apart. This is a process of renaming the variable in logical expression so that each variable has a unique score. So thereby avoiding unintended variable clashes during unification. And that means the renaming variables does not change the meaning of the expression. So here we will see the example. We will discuss with the example that standardization part. We will discuss with an example. Here in the previous slide we have already seen that is knows John comma x. That is the one expression, and the second one is knows x comma Elizabeth. X comma Elizabeth. So The problem was the x cannot take two values at a time. That is, it's in that case x can be John, x can be Elizabeth. So that is not possible. So here we can modify it. That is, unification failed in the previous case. That means the first argument x can be John and the second argument x can be Elizabeth. A variable cannot be bound to two different constants. So we are applying standardizing apart. So that means rename the variable in the second expression. So we here you can see here it is renamed as y. So it will become, the second expression will become knows y comma Elizabeth. So here in this case you can see if we are comparing these two expressions, unified John comma knows John comma x and knows y comma Elizabeth. Here you can see y can be John and x can be Elizabeth. So the substitution is possible. So now unification now succeeds and meaning of the expression is unchanged. So this renaming process is called standardizing apart. So the variable names are local symbols. So renaming them does not change the meaning, but it prevents the clashes during unification. And in some cases, multiple possible unifiers. So that means in some cases, more than one unifier can satisfy the condition. Here you can see that in the example, unify knows John comma x and knows y comma z. So this is the example. Here the unification, the first unifier you can see that here y can be John and x can be z. So here the unification theta 1 equal means y slash John and x slash z. So then you can see here the next unifier. There you can see that y can be John, x can be John and z can be John. So these are the unifiers here. So that means here knows John comma x and y comma Elizabeth. There x can be John and there y can be John, and also when we are comparing this, when x is John then it is compared with the z, then z can also be John. So the resulting expression will be knows John comma John. So here among all possible unifiers, here we have to make the fewest commitments actually. So that keeps the expression as a general as possible. So the renaming variables to ensure unique scope and avoid clashes during unification without changing meaning. Here we will discuss about the rules for matching. So the matching determines whether two expressions can be made identical by applying valid substitutions. Here we will see the rules. The first rule is different constants, functions or predicates cannot match whereas identical ones can. So here you can see the example John and Mary. So John and Mary are two different constants, so we cannot match them. Then knows x comma y. There knows a comma b. There you can see here x can be a and y can be b. So matching is possible. Next one is likes x, hates x. Here one predicate is likes and another predicate is hates. So we cannot match them. The second rule is a variable can match another variable, any constant or a function or predicate expression, subject to the condition that the function or predicate expression must not contain any instance of variable being matched. Otherwise, it leads to infinite recursion. So that means a variable can match to another variable, a constant, a function or a predicate expression, but there is a condition that the expression must not contain a variable itself. So otherwise it leads to a infinite recursion. Here in this example you can see x can be John, x can be f of y, and that is also valid. When x is equal to f of x, that is invalid. That occurs check violation. And the third rule is substitution must be consistent. That is, substituting y for x now and then z for x later is inconsistent. So that means once a variable is substituted, the same substitution must be used everywhere. So first x is substituted as y, and later X substitute as Z is inconsistent. So substitution must be consistent throughout. Here we will see the algorithm of unification. Here we are considering two variables are constant L1 and L2. So when if L1 and L2 are identical or both are identical, then it will return nil. So that means already see there is no need of substitution is required. And in B you can see else L1 is a variable and L1 occurs inside L2. So that means fail. For example, you can see here, here if it is unified, one is x and another one is f of x. So it is not possible for substitution and it will return fail. And second is next case, that means else case, substitute L1 with the L2. That is possible. Substitute L1 with the L2. Then else case, L2 is a variable and L2 occurs inside L1. So it is here we can consider unify f of x comma x. So it also return fail and else case here L2 we can substitute L2 with the L1. Then else case it return fails. So then here you can see if that means it can be in D case it can be both can be constant but not equal. So in that case it will return fail. And step 2 we have to check predicate symbols. So if the initial predicate symbols in L1 and L2 are identical then are not identical then it will return fail. For example, if first one is P of x and second one is q of x. So then P and Q are different predicates, so it is not possible for any substitution. Then step 3, if L1 L2 have different number of arguments, then also it will return fail. So if we have unified P of x comma y, that is one expression, and second expression is that is P of x. Predicates are same, but you can see here we have two arguments. Here there is only one argument. So it returns fail. Then the fourth step is initialize the substitution. So here we are considering set as substitute is equal to nil. So it will store all substitutions made during this unification steps. Then first we will see the arguments by we will declare an loop. There we are considering for each argument position as I. So initially we are taking I is equal to 1. Then we will take each argument one by one. So if fail means that we have to call unify with ith arguments of L1 and ith argument of L2 and putting the result in substitute. So here that means S and here S contains fails means then it will return fail. So f is not equal to nil, then we have to apply to the remainder. That means remaining arguments of L1 and L2. So apply to the remaining arguments and add to the substitute. And each time we are appending this to the substitute. Appending S to the substitute. Then the sixth step, that is return substitute. So here in this unification is actually used in resolution and forward backward chaining. Unification is a process of finding the substitution that makes two first order logic expression syntactically identical. Thank you.